The basic ideas of neural networks have already been discussed by Dr. Mishra. I'm not sure if you have tried any code using neural network, but today we will explain that once again, and we'll show some simple examples with materials. So today's lecture, as far as the explanation of the neural network idea and how to construct neural network, how to write that code using something called PyTorch, will be explained by my student Saurabh Mal, who is also a TA for the course. So I'll hand it over to him. So he will explain to you how to, the ideas of neural network.
Okay, so how do I know they're hearing me or not? Okay, can you hear me?
Just type in if you can hear us clearly.
Okay, so let me start. So our goal is to predict formation energy of crystalline materials using neural network, and our input will be sign matrix eigenvalues. So here I'll briefly summarize the architecture of neural networks. So first there will be input layer. So here, for example, in the input layer there are three neurons, and at the end there will be output layer, and it's basically the property value we are trying to predict. For example, here formation energy. Now, as input we are using sign matrix eigenvalues. For example, if we use 10 eigenvalues, then there will be 10 neurons in the input layer. Now, in between input layer and the output layer there are several hidden layers, and each neuron in hidden layer is connected to all other neurons in the previous layer and the next layer of it. And the output from one layer is used as input to the next layer. And such network architecture is what called feed forward neural network. And the question is what a single neuron is doing here. It essentially performing three operations. First, it takes the inputs x1, x2, x3. Let's assuming it's connected to three inputs, and then each input is connected to the neuron with some connection, and it's called the weights. So there are three connections, so there will be three weights, w1, w2 and w3. So first it will take the inputs, then it performs the weighted sum of its inputs and adds a bias. So this is the step, sum over I wi xi plus b, and then this value will be passed through some activation function sigma. So final output from a neuron will be sigma of z, where sigma might be the sigmoid function or ReLU function. These two are most widely used activation functions depending on the task, depending on classification or regression, etc. Now to train the neural network, so there will be trainable parameters. Now here the trainable parameters will be the weights, which are basically the connections, and the biases of each neuron. And to do that, we have to minimize some cost function. Here we will predict the formation energy. So this is regression task, and for which we will optimize the mean squared error. the formula is this. So it's essentially is the difference between actual output and the predicted output. Okay, let's go ahead with the actual coding part of it. So first we'll import several libraries. The standard one are pandas, numpy. For plotting, we'll use matplotlib. For data handling, for example, train test split and feature feature scaling, we'll use the scikit-learn's inbuilt function. And we'll build the model here using PyTorch. So you have to import the PyTorch object like this, import torch. For neural network, you have to import torch.nn as nn. And to prepare the data for PyTorch, you have to create something called data loader object or tensor dataset. And for model evaluation, we'll be using scikit-learn's inbuilt metrics like mean absolute error R2 score. To get familiarity with the PyTorch environment and its data loader or tensor dataset objects, I will recommend to follow this particular website. So, is it coming?
Sharing the entire screen or sharing a window?
Oh, I'm sharing a window. That's why it's
Okay,
not
so
showing.
to go out and share. It's better to share your entire screen if possible.
Okay, then stop sharing.
Now you can stop sharing.
Share. Should I share entire screen? Okay, so for the familiarity with PyTorch datasets and data loader objects, I will recommend to follow this web page. This is basically the PyTorch official documentation of the how to prepare datasets and create data loader objects to train models. Okay, so let's get back to the coding part. So also I'll recommend to set up the environment. Hmm. So I'll also recommend to set up the environment here using maybe Python 3.1 or 3.11. Create some environment and make sure that you have installed all the necessary torch libraries. So pip install torch, torch vision, torch audio, and also install all the libraries numpy, pandas, scikit-learn, matplotlib, and other things. So once you will be done with this, let's go ahead. So here, have you shared this data set with them? Okay, so it's known already.
The which is the band
This band gap ASM data set.
Yes.
Okay. So here we will be using this band gap underscore ASM dataset, and in this dataset, the total number of materials is 1592, and these materials are basically there are maximum 10 number of atoms in the unit cell. So the size of sign matrix will be 10 cross 10, and there will be 10 sign matrix eigenvalues. So the input to the model will be 10 sign matrix eigenvalues, and the output will be taking the formation energy per atom. So to prepare the data set, first we are shuffling the CSP. Yes, it's open now.
So let me see. So apart from the eigenvalues, can you go to the right? Yeah. So apart from the, so you see there is some missing columns because I think when I created the headers were created assuming that there are 12, maximum of 20 atoms in the unit cell, but uh, but okay. So, um, Good question.
Hmm.
But actually, there are 10. So, therefore, the last 10, eigenvalue 11 to 20, there are no numbers there. So, of course, you have to drop those columns when you train your model. Then there are three physical quantities which are simultaneously written out in the file: the band gap, the formation energy per atom, and energy above the hull. So, here is that is the structure of the data set. So now Saurabh will go ahead and show you how to use it, and we'll see what performance we get out of this model for prediction of any of these quantities. So we can start with uh, band gap or maybe formation energy per atom.
Yeah, so here I'm using the formation energy per atom.
But this dropping of the uh,
Yeah.
hmm, dropping of the columns, just go to the data file once more.
Yes.
So go to the left, some stop there. So you have numbers only up to eigenvalue 10, 11 to 20. These are empty.
Yes.
So those columns have to be dropped from
Yes.
data. So I think that I'm not sure that is the correct version.
Yeah, we have to done it because these are in values, so there will be errors.
Hmm.
So, for example, here in this line, I have selected the features up to the 10th eigenvalues. So, how to do it? I have selected all the rows, that means all the materials, and for the columns, I have selected from
I like that line.
2 to 12. So, it's basically the 2 to 12th column are essentially containing the first 10 eigenvalues of each material. And so this is the target. This is the feature X.
So this you have to know your data file, that which are the columns which contain meaningful data that you want to use.
And here we are using formation energy per atoms as the target. So in this line, Y equals to data, and then we are selecting the formation energy per atom column, and this will be our target. And we are converting the X to numpy array like this. And this is the requirement to perform train test split using the scikit-learn's train test split object. So in this line, we are performing the creation of training set and test set, and we are using 80 is to 20 random train test split, and this line will do that. Now, for any machine learning task, we have to scale the data, both input and both target and the input features. Now here we are using quantile transformer for both the features and the target. And for example, here this x scalar equals to quantile transformer and dot feed underscore. I mean, it is fitted on the training set, and then we are using this x scalar object to transform both the training set and test set features. And also similarly, we are performing the scaling operation on the target y, and it is fitted on the training set, and then we are using that y scalar object to scale both the training and test target.
So these are exactly the same as what we did when we trained the linear or the random forest models. Data scaling is a very usual thing that you do in most machine learning tasks.
And yes, and these are basically the common tasks before performing any machine learning model. I mean, it may be random forest or any other model. It's common to all the models. Now, this is the crucial step to. So this is the second thing. We have to create PyTorch loader object to load the data, and this is the requirement for PyTorch only. And so first, we are converting the expense scaled object to torch object for both training data, test data, and also the targets. And then finally, we will be creating the data loader object to load this data. And PyTorch models will load the data from this data loader object. And here you have to specify one crucial object or quantity which is called batch size. And here we have used batch size equals to 64. Yeah. So we have specified batch size equals to 64. And basically, if we have mm, 1000 materials, then there will be n number of batches, and each batch has 64 materials. Now, this is the third step. Here we are building the models. So first you have to import the torch object, import torch and import torch.nn as nn. And here I am defining a class object called regressor nn, and which is coming from nn.module object. Now here I am implementing a simple multi-layer perceptron for this regression class, and our input is 10 features, 10 sign matrix eigenvalues, and our output is just the formation energy. So here we are doing a mapping from 10 features to a single output. So in the input layer, there will be 10 number of neurons, and in the output layer, there will be just a single neuron to produce the formation energy. And in this architecture, we are also including batch normalization and dropout rate regularization, which are very suitable for small dataset to avoid overfitting. Specifically, batch normalization, it standardizes the output of the linear layer to stabilize training dynamics, and dropout layer we are using at zero point 0.2, which means we randomly turns off 20% of neurons during training, and this stops the model from memorizing the data and forces it to learn the underlying patterns instead. And there will be two building blocks in the neural network architecture for each layer, and the structure of each block is the following. So first there will be linear layer, then the output of this linear layer will be passed through batch normalization, and this output will be passed through a activation function, and here we are using ReLU activation function, and finally it will be passed through the dropout layer. So how we are doing it? So you have to create this module, and you have to specify the input size, which is 10 here, and I have used two hidden layers. So hidden size 1, there will be 32 neurons, and in the second hidden layer I have used 16 neurons, and the dropout rate I have used is 0 0.2. Now all these numbers are basically hyperparameters from the model, and we have to fine tune it to get better results. For the demonstration purpose, I have used these numbers only. Now let's come back to the first layer. So in the first layer, so it will be nn.linear layer, that's the basic layer, and there will be number of input neurons will be equal to the input size, and it will be mapped to a hidden layer with number of hidden neurons, which is here hidden size 1, which is here 32. And then in the layer 2, again there will be nn.linear layer. The input number of inputs will be hidden size 1, which is 32, and it will be mapped to hidden size 2, that is 16. And then again we have defined the batch normalization in this layer also. And finally, the output layer, it will connect it to the hidden layer 2. So basically there will be 32 neurons, and it will be mapped to a single neuron 1. And I have defined the activation function throughout the architecture as nn.relu, and after each layer I will apply dropout layer, which is defined by this nn.dropout rate. So to do the forward pass, the input will be x, then it will be passed through the block 1. So this x will be passed through first fully connected layer, then the output will be passed through batch normalization, which will be passed through the activation function, which is ReLU, and finally the dropout layer. And then this output will be passed to the block 2, which is first the hidden layer 2, and then the batch normalization, activation, and dropout, and finally this output value will be passed to the output layer, and then it will return the X object. and this x will be basically the predicted value. Now to train the model, you have to specify some device, and the device object is defined like this: torch.device. If you are using GPU, then you have to use CUDA. So CUDA, if torch.CUDA is available, otherwise CPU. So for example, I am running this code in my laptop, and it will be just CPU. And then you can count the total number of trainable parameters here. For example, here the trainable parameters will be the weights and biases of the neurons. So for this specific architecture, total number of trainable parameters is 993. Now let's come back to the training the model. So first you have to specify the learning rate. So we'll be using gradient descent, or more specifically an advanced version of gradient descent using Adam optimizer. And for that, we are using the learning rate 1 e to the power minus 4. And the loss function, it is defined here by the term criterion. We are using the mean squared error loss. Okay, just a minute. Let's run all these code snippets. Setting up device. Okay, so now we'll train this model. Now let's go slowly with this training phase. So we have defined two lists to train loss epoch and teach loss with epoch. So for each epoch, we'll basically save what is the training loss and teach loss just to visualize it later. And we are using total 400 epochs here. And to check how much time it will take to train the model, we will use this time variable start time. Now for each epoch, there will be two parts. One is training phase and another one will be test phase. Now in training phase, this is the PyTorch objects functionality. You have to call this model.train object, and then you have to load the train loader that's already loaded. Now how it works? For each epoch, we have already loaded the train loader object, so the model will uh, do the things for each batch. So how we are processing the batches for data and target in TQDM train loader thing. So it will parse each batch and the corresponding target value, and then you have to load this value to the device object and also the target. Then you have to do the forward pass. So model, so it will take the data value. So you will get the final output. So this output is basically the predicted value of the property. So here the formation energy. So it will take the data and the model output will be the output. And then you will calculate the loss function here. So we have defined the mean squared error loss. So it will calculate it between the output and the target. So here the target is the actual value and the output is the predicted value predicted by the model. And then you have to accumulate all the batch losses. And then when you summed up all the training loss for this particular epoch, you have to perform this back propagation to optimize the weights and biases using the Adam optimizer. So in the training phase, you have to use this optimizer.0 underscore grad and then perform the back propagation. So loss.backward will perform this back propagation operation, and this optimizer.state object will update all the weights and biases of the model, and then you can save these loss values to the lists that we have defined earlier. And similarly, in the test phase, you have to do this operation in the test data, but this time there will be no gradient calculation. So it will just take the data, predict the value, and you calculate the loss and save it. And at the end, you can also save the model by this line torch.save, and then load all the trainable parameters that we have optimized using this gradient descent method, backpropagation method. So model dot state underscore date, and you will give it a name. For example, here I have given it nn dot pt, and at the end I'm printing it how much time it will take to train this model. So let's train it, and here you can see the training is progressing for 400 epochs, and it's printing for each epoch what's the training loss and what's the test loss. So to train this architecture with 400 epochs, it took 19, roughly 19 seconds. And
this is on a CPU?
Yeah, this is on a CPU in the laptop. And then you can just store the number of epochs, number of and the values of training loss and test loss to later visualize how the training is progressing. So I have saved it here, and then you can plot the learning curve. And here this is the learning curve. So the orange line is for test loss, the blue line is for training loss, and interestingly here training loss is higher than test loss, and which is basically, I mean, general observations for small dataset with highly regularized model. For example, here the dataset size is only 1,000, and we have implemented batch normalization and dropout here. So these regularization things are there, for which sometimes this may happen that the test loss is lower than the training loss. So there is no overfitting. Now, to evaluate the model performance, you have to use this model dot, you have to call this model dot eval object, and then I have predicted in the training set first. So this line, so model and then x train scale that we have already spent data, we will predict the target y train rate, and then importantly, since we have scaled the numbers of the target, so the scaling is changed. So you have to inverse it back to the original scale to get a meaningful answer. So this y scalar dot inverse underscore transform will do this task. So if we start with uh, EV per atom, at the end, after this inverse transform, our final unit of formation energy will be EV per atom. And similarly, I have done the same thing on the test data also. So pass it through the model, calculate the output, do the inverse transformation, and get the predictions. And once we are ready with this, now we have the actual value and the predicted value. So actual value for the training set is y train, and the predicted value is y train rate. And now you can calculate the mean absolute error and the R2 score.
No, these are functions that come from scikit-learn, right?
Yeah,
We have imported these from scikit-learn.
yeah. So for training set and test set, we can calculate these two quantities. Sorry. Yeah. So for example, for this particular instance of training, the training set mean absolute error is 0.63 EV per atom, with training R2 is 0.38, and the test set, these numbers are 0.6425, and test R2 is 0.3863.
So you see the R2 scores are not particularly good. They are only about 0.38. Firstly, the data set is very small.
Yeah.
So it's not enough to train a good model.
And specifically in this neural network model.
Specifically neural network. So what we'll do next is we can try. So I have, yeah, you go ahead.
Yeah, then I mean,
Then I'll
we can get this parity plot showing how things are going on at the prediction levels. So at the x-axis there are the actual values for formation energy, and the y-axis there are the predicted values. So these are the scattered plots, and it's not good prediction. The ideal prediction will follow these dashed lines with R2 score 1. Yeah.
Yeah, so one thing let me point out is that whenever you are doing a regression model, you are predicting a particular quantity. It is almost customary to plot such parity plots, actual the predicted values as function of actual values, which gives you a visual guide or visual indication of how well your model is doing. And of course, in the ideal case, you would have a straight line with zero intercept and a slope of 1.
Yeah.
But of course, in real life, that never happens. But how much your predictions deviate from this straight line is an indication of how the model is doing. And here you see there are both the test and training set examples are plotted here. And even for the training set, the blue dots, the prediction is not good. And of course, it's not good for the test set. So this is not a good model. The neural network didn't get trained very well because the number of data points is very small, which is overall data set was what 1500 something, and then it was split. So 80% of that was used for the actual training.
And also, I haven't fine-tuned the model. These are
The
just
model is not fine-tuned. Here, fine-tuning means what is your architecture, how many hidden layers you would have. See, what you have to be clear about is that your input layer, the number of neurons in the input layer is fixed by the size of your feature space, the dimension of your feature space. Because we are using 10 eigenvalues of the sign matrix, that has to be 10 neurons. But after that, how many hidden layers you have and what are the number of neurons in each layer is the the most important part of the important hyperparameters for a neural network. So the width and the depth that Shivankar Mishra has explained to you, these are not given, so you have to do some. The easiest way for such simple problems is to do some tests and figure out what is the optimum. Uh, then, of course, the dropout rate is another quantity that one can.
and also the activation function.
Yes, the activation function and the dropout rate, changing these, how your model performance changes. So these are things that one has to experiment with before arriving at a particular uh, architecture. Okay, in the meantime, so I have made to you another code, very simple. It's just a simple modification. I mean, trivial modification of this particular code that Saurav was showing you, and a data set that you are already familiar with. It's the data set for data formation for the ABAC free materials. So the task for you is to use that code as it exists. It reads in from that heater formation data set of the ABAC3 materials and run it and see what kind of performance you get, whether you get good performance or bad performance. Well, I'll give you some time to do it, but the first thing you do is if you are um, if you are online, then just open it. I sent you over email while the class was on. So you should have that file which is named, let me check the name. Okay. ANH for ABS dot py. So that Python script. So you just someone, I'll give you 2 minutes. If you can write to me, write on the screen, or you can tell us by switching on your microphone that what is the architecture of that model, how many hidden layers you have, and what are the number of neurons on each in each hidden layer. So I'll give you 2 minutes for that. Yeah, if you have the answers, you can write it on the chat box. In the meantime, we'll open the data file. Yes, now go to the right. So the first column is of course materials, then the eigenvalues. And you are familiar with that this file. I have shared it with you. I have shown it earlier. So there are 30 eigenvalues. So this data set was created keeping a maximum of 30 atoms in the unit cell. So there are 30 eigenvalues of the sign matrix, and then the heater formation of ABAC3 type of materials. So therefore, because my feature space is 30 dimensional, I have to have 30 neurons in the input layer. So now go to the code. Yes. Just highlight on that definition line. Yes. No, the one after that definition.
Oh.
Yes. So this is where the model is defined, and now you see the input size is 30 neurons in the input layer. The number of layers is kept the same. Hidden layer 1, hidden layer 2, then the output. And there are 64 neurons in the first hidden layer, and then 16 neurons in the second hidden layer, and then the output layer. And if you see the structure of the neural network, the dropout has actually not been used in this case. Is it a good architecture? Maybe not. So the task for you would be to try to optimize the architecture. Do you need more input layers? Do you need layers with the more neurons? So that is something you can experiment with and tell me next time in the next class. In the meantime, we can run and see how it performs. Let's see if it works.
This code. Just wait from. What's the name of this file?
ANN H underscore H form. Yes. Yeah, so that's how it goes. That's the learning curve, 200 epochs. And finally, what are the scores matrix? Let us see. Yeah, it doesn't look very good to me. What are the numbers?
It's better than the.
Can we see the numbers? R2 score? No, R2 scores are of the same order.
But mean absolute error is smaller.
Slightly smaller.
0.6 dB per atom, now it's 0.29.
Yes.
Almost.
So maybe because see, one thing is this data set is much bigger. This has some 5,000 plus materials. So that is why the training, maybe that is why the training is a bit better. But then it has to be made even better. So therefore, your task will be to play with the hyperparameters and see if you can improve it. Okay, so that is your task for the next day. And so that is it. The other thing that we will discuss, not today, so this is enough. I have already sent you this. The previous code is very similar to this. I'll share that with you also. And your task is to, and that band gap data set is already shared with you. Can we just see how that previous code function works for the band gap data set? Just change that. Yeah, so while we do that, what I want to mention is that next time we will discuss one of the pictorial representations of materials, and we'll see how it's particularly suitable for neural networks, not that you cannot use it for other models, but it's particularly naturally suited for neural network. So we'll see how a neural network trained on that pictorial representation performs for various property predictions. Okay, so what we're trying to do is to see how, so far we were training the models for formation energy prediction. Now we are trying to train it for band gap prediction.
It's not doing great on band gap quantity. There is a huge gap actually.
Yeah, there's a big gap between the training loss and the test loss, which
so the test loss quickly saturates to 1.10.
There's some overfitting may be happening.
Yes. So negative address. So it's doing nothing essentially.
Yes. So too few data points. It is not predicting anything. It's a flat line. So it does very badly. But you can, I had suggested that you create a bigger data set for band gap, with keeping materials that have more atoms in the unit cell. That would give you a bigger data set. You can try training it for band gap prediction, but I don't expect sign matrix eigenvalues to do very well for band gap prediction. But because this doesn't take much time, you can try that out. And of course, the other task is to try neural network and optimize its architecture for the data set of heater formation of the ABAC3 materials. So that is all for today. There is nothing more that I want to tell or show you today. If you have any questions, you can ask. I'll give you a minute. Otherwise, we'll meet on Friday.